Hey everyone, and welcome. Today, we're going to pull back the curtain on one of the biggest secrets in technology. It's this one simple principle that explains a frustration I know we've all had, why some computers feel absolutely blazing fast, and others, well, not so much.
So let's kick things off with a mystery. And I'm pretty sure you've been here before. You install a new app on your friend's top-of-the-line PC, and it's just seamless. Then you take that exact same program, install it on your machine back home, and suddenly you've got enough time to go brew a fresh pot of coffee while it's loading. What is actually going on there? Well, the answer to that little mystery, it's not as simple as just saying, oh, it has faster parts. To really get it, we've got to go deeper. We need to look at the relationship between the program itself, the software, and the actual physical machine it's running on, the hardware. Okay, so a great way to think about this is like building a house. On one hand, you've got computer architecture. This is basically the architect's blueprint, right? It's the grand design, the plan, what the house should do. Then, on the other hand, you have computer organization. And that is the actual construction. We're talking the specific bricks, the way the pipes are laid out, the physical reality of the building. So let's zoom in on that blueprint first. Computer architecture. That's everything a programmer needs to know to get their software to work. It's the rule book for the system. Like, what commands can it understand? How does it manage data? How does it get stuff from memory? It's all about the logical design. You see, when an engineer is working on the architecture, they aren't thinking about wires and chips yet. Not at all. They're asking these big, creative questions like, what's the whole point of this computer? What should it be able to do? Okay, now let's flip over to the other side of the coin, the construction. Computer organization is all about how it's physically put together. We're talking the real nuts and bolts, the actual memory chips they chose, the way it's wired, the signals that make that blueprint a reality. It's not about what it does, but how it physically gets the job done. And yeah, that really nails the difference, right? Organization answers a totally different question. How does this thing actually work? It's the nitty-gritty details of all the physical parts working together to bring that architect's dream to life.
Okay, so we've got the blueprint, the architecture, and we've got the actual building, the organization. So how does the software, which is designed for the blueprint, actually tell the physical machine what to do? There's got to be some kind of translator in the middle, right?
And there is. That translator is called the ISA, or Instruction Set Architecture. A good way to think of it is like a contract between the hardware and the software. It's the official language they both agree to speak. The ISA is what lets the software talk to the machine and tell the hardware precisely what it needs to do. Now, this all seems pretty simple, doesn't it? You've got the physical machine, and you've got the programs running on top of it. Easy. But what if I told you that that clean line we all draw between hardware and software, what if it's not real? What if it's kind of an illusion? And that brings us to the big secret, the core idea of this whole explainer. It's this really mind-bending concept called the Principle of Equivalence of hardware and software. Now listen to this, because it's a big one. It says that any task you can do with software, you could also do by building a specialized piece of hardware. And the other way around, anything a piece of hardware does could also be done with a piece of software. Basically, they're interchangeable, assuming, of course, that speed isn't a concern. And look, this isn't just some abstract theory. It's a real, practical choice that engineers have to make every single time they design something. To show you what I mean, let's take a look at an example you've probably got sitting in your kitchen right now. Yeah, your microwave, the little computer inside it, that's a hardware-based solution. It's a special little system built to do one thing and one thing only, run the microwave. But you could, 100%, write a computer program to do all the exact same things. That'd be the software-based solution. See? Two totally different ways to get the same job done.
And this choice right here is what solves our original mystery. The reason your program is slow isn't really about the software, it's about the hardware's organization, the choices the engineers made. On your friend's super-fast PC, the engineers probably built a special function right into a chip, hardware, that makes it lightning fast for that specific task. On your machine, maybe they decided to use a more flexible but slower software approach to do the same thing. Neither one is wrong. They're just different trade-offs. And that's the constant balancing act for engineers. Do we go for raw speed with hardware, or do we go for flexibility with software? So when you boil it all down, understanding this relationship, the difference and also the sameness between the blueprint of architecture and the physical reality of organization, that's what gives engineers their power.
It lets them make the absolute best call for whatever they're building. And that is how we end up with the faster, smarter tech that, basically runs our lives. So that leaves us with one last kind of cool thing to think about. If we know that for any problem, we can choose to either build a machine or write a program, what are the next big problems we're going to choose to solve? And more importantly, which path will we take to get there?